Hey everyone, in this video we're going to go over the example from video 206 on the superposition principle. We're going to work on this together. So first of all, let's look at the steps to solving these types of problems. What we're doing is we're adding forces to find a net force on a charge. So I'm just calling this type of problem electric force problems. I'm just generalizing. And so these are going to be the steps that we're going to follow every time that we solve these types of problems where we have more than one charge and we want to figure out what's the net force on one of the charges. So the first step is going to be to label all the charges. The next step is going to be to draw and label the forces and then calculate each force. And actually, we're going to go through all of these steps as we do the example. That's going to be a lot more useful. So let's take a look at this example here. It says, find the net force exerted on the 0.8 microcoulomb charge. So the first step was to label the charges. So let's go right here and let's call this charge 1, charge 2, and charge 3. Alright, the next step, if we go back a couple of slides, draw and label the forces acting on one charge due to each other charge. So we're trying to find the force exerted on this charge up here. So there's going to be a force on this charge due to this one and also due to this one. And let me actually redraw this because there's just not that much room up there. So we've got number 1, number 2, and number 3 here. So 1 and 2 attract each other. We're just drawing the force on number 1. That's the one that the question is asking about. So even though you might want to draw a force like this because they are attracting, that's fine. But we only care about number 1, so we're not even going to draw any forces on number 2 or 3. And then 1 and 3 are repelling each other because they are like charges. So we're going to draw a repelling force. And remember that the direction of this repelling force is along that straight line joining the two charges. So this one here, we're going to call it F21, the force from charge 2 acting on number 1. And this one here, what do you think we're going to call it? F31, the force from number 3 acting on number 1. So hopefully, as we talk about each step, you pause the video and try to do each step by yourself before we go over it. Let's look at the next step, number 3. It said, calculate each force using Coulomb's law. We have two forces that we have drawn, so now we want to go ahead and calculate them. So go ahead and try it. Pause the video. Let's give it a try. How do we calculate F21? Well, it just uses Coulomb's law. The force between any two charges is going to be K, Q1, Q2, over R squared. It doesn't matter if you write 1 and 2 or 2 and 1, you're just multiplying them, you'll get the same thing. So the distance between the two charges is what R is. So we do have several distances here. We do need to make sure to use the correct distances. So this distance here is a distance between 2 and 1, while this distance over here is the distance between 3 and 1. So instead of calling it R, let's call it R21 just to make sure that we are using the correct distance. If we look at the picture here, the 8 centimeters is the R21. Now, we do want to always have all distances in meters. So let's go ahead and rewrite these R's here. So R21 is going to be 8 centimeters. Divide by 100 to get your meters. Move the decimal places 2 to the left to get 0.08 meters. Remember, centi is 10 to the negative 2. So that's 0.08 meters for R21. Q1 and Q2 are over here. This is Q1, 0.8 microcoulombs. Remember, micro is 10 to the negative 6. So 0.8 times 10 to the negative 6 is the number here, and then Q2 is negative 0.6, but remember that there's absolute values here. We only care about the magnitude of the charge. So we can still put the negative in, we can just ignore the negative because it's going to go away with the absolute value. What we really care about is the number, which is 0.6 times 10 to the negative 6 coulombs. While we're here, let's go ahead and finish our givens here. Q3 is 1 microcoulomb, or 1 times 10 to the negative 6 coulombs. And then, let's not forget this distance here, R3, 1, the distance between 3 and 1, is 10 centimeters, with the decimal 2 to the left to get 0.1 meters. Okay, so now I leave you to calculate the forces between these charges. So let's just plug in all of the numbers. K was Coulomb's constant, 8.99 times 10 to the 9. Don't worry about all the units. As long as you're in meters for the distance and coulombs for the charges, you will end up with newtons for your unit for your force. So you don't have to worry about putting all the units in here. So we're going to put in 0.8 times 10 to the negative 6, and then 0.6 times 10 to the negative 6. And it's good to practice just to make sure that you can use your calculator correctly. And then for the distance, I'm going to put 0.08, and don't forget to square that. That's a common mistake, forgetting to square that distance. So if you put all of that in correctly, then you should get about 0.674 newtons. So as always, I'm going to round on the screen, but as I'm calculating all the values, I always use the unrounded values. So hopefully you got that. And let's go ahead and do the other one. The step number 3 said calculate all the forces that we drew. We just calculated F21. Now we need to calculate F31. So we're going to do K, Q1, Q3, right? This would be now the force between 1 and 3 instead of the force between 1 and 2. You can put any two charges here depending on what force that you're solving for. So this is the force between 1 and 3, or 3 and 1. And then you need to put the distance between those two charges. So we're going to put R31 squared in here. And then we're going to go ahead and plug in all of the values. 8.99 times 10 to the 9 for Coulomb constant. 0.8 times 10 to the negative 6 for Q1. And then 1 times 10 to the negative 6 for Q3. And then the distance was 0.1, so we're going to make sure to square that value. And that's going to give us 0.719 newtons. Okay, so this was step number 3. Let's take a look at the next step. I'm going to hide my video so I have a little bit more room. Right? So step number 4, use vector addition to find the resultant force. So this has many steps. The first step is to find the x and y components of each force. So let's look at our two forces. We have one force that is straight down, so it only has a y component. And then we have one force that is to the left and upward, so it has an x and a y component. So whenever I find my x and y components, I like to draw a little table to really separate those. So I'm going to go ahead and do that on the next slide to make sure that we have plenty of room. Okay, so I'm going to draw a little table, x and y. I've got two forces, and we can just redraw this picture right here. So we have it again. We have one force this way, F31, and then we have one force this way, F21. So what I like to do when I'm finding those x and y components is go ahead and write f21x and f31x. Just write down the x component of each force, and then write down the y component of each force, f21y and f31y. Just even if they're equal to 0, I just like to have that placeholder so that I don't forget anything. And then you look at each force one at a time, and you write down what you know. So F21 was going straight down. It did not have an x component. It's only going vertically. It only has a y. So that means that the x component is 0. The y component is going down, so it's going to be negative, but it's going to take the full value of F21. So it's going to be negative F21. And we found F21, which was 0.674. So negative 0.674 newtons is F21y. And I don't bother writing the units just because it takes up a lot of room. Not that much, but I like to try to keep it as neat as possible. Alright, so F31x and F31y. So F31 is diagonal. We want to draw the x and y components. So we know that to get from here to here, we have to go to the left and then upward. So this is F31x to the left, and then F31y upward. To find these components, we need an angle. Now, we're not given an angle, so we have to do a little bit of extra work to find the angle. So this angle right here that we need, if we look here, it was because of this line here. This angle that we need here is the same one as this angle here. So what we can, because they're, corresponding angles, you have two parallel lines, forget exactly what it's called, but definitely recognize that these are the same angles. So to find this angle, we can use the geometry of the triangle. We can forget about the forces for now and just look at this triangle and use the geometry, the actual distances, not the forces, to find the angle. Let's call it theta. So if we're trying to find theta, and we know that the side opposite of theta is 8 centimeters, and the hypotenuse is 10 centimeters. We know that the sine of an angle is equal to the opposite over the hypotenuse. So we can use that trig function definition to plug in what we know and solve for theta. Sine of theta is equal to 8 centimeters over 10 centimeters. Right? Opposite over hypotenuse. This is the opposite. This is the hypotenuse. So the centimeters cancel out. We have sine of theta equals 8 over 10. In order to find theta by itself, you need to do the inverse sine to get theta by itself. When you do the inverse sine of both sides, it will cancel out this sign over here. So you'll get theta on the left-hand side. And on the right-hand side, you have the inverse sine of 8 over 10. So that's how you get the angle by itself. And you plug this in the calculator, and you're going to get about 53.1 degrees for this angle. So we just used geometry to get this angle. And now using geometry and trigonometry, right, to do this angle. Now, using geometry here, this angle that we care about happens to be the same one that we found. So now we know the angle. Usually we are given an angle. This was just an extra step in this problem. It's a good review of using your trig functions. Okay, so now that we know the angle, how do we find F31x? Go ahead and pause the video and write down the two components for this force. Okay, so the way that you write down the components is you write down the hypotenuse first, which is F31, and then you think about, is the side that I'm looking for, is it opposite or adjacent? So 31x is adjacent, that uses cosine. So F31 cosine theta. And then you also look at the direction of F31x is going to the left, So that's going to be a negative component, a negative force. That's how you find a component. Then you plug in everything that you know, negative 0.719, cosine of 53.1 degrees. And if you don't round anything, you should get negative 0.431 newtons. Okay, can you do the F311 by yourself? If so, pause the video. Let's take a look. F31y is opposite theta, so it's going to use sine. So F31 sine of theta, and it is going up, so it is positive, so we're good here with the positive. Plug in everything, 0.719 for F31, put sine of 53.1 degrees. Plug all of this in the calculator, and we're going to get 0.575 as F31y. Okay, so I know it's a lot of work, but we're just breaking it down step by step. Let's look at our next step. The next step is add all of the x components to get f of x, and let's look at C, add all of the y components to get f of y. So let's do both of those steps. We have found all of these components. We're going to add all of these x components to get f of x. Remember what f of x is? It's the net force in the x direction. So 0 plus negative 0.431 will give us negative 0.431. And then we're going to add all of the y components to get the y component of that net force. Negative 0.674 plus 0.575, that's going to give us negative 0.099 newtons. All right, let's look at the next step here and use the Pythagorean theorem to find the resultant force F, and then use inverse tan of negative Fy over Fx to find the direction. So let's go back to our example, take a look here. Alrighty, so before we do that, I actually like to draw Fx and Fy, just so we have an idea of which way this net force is going. So Fx is going to the left because it's negative. And then Fy is going down because it's also negative. So these are the x and y components of the net force that we just found. And that is why we can use the Pythagorean theorem to find F, because F is the net force, and the x and y components make a triangle so that we can find F. To make a right triangle, we can use the Pythagorean theorem to find that net force. Let's go ahead and write it down here. F equals the square root of fx squared plus fy squared. Plug in all of these values here, and since I don't have too much room, I will let you plug in this value and this value. They're both squared, so the negative doesn't matter. The negative will cancel out. So when you square both of these and add them up and take the square root, we're going to get 0.442 newtons. At the end, I do like to put a unit. The force is always in newtons. So that's the net force. And then the last part was to find that direction. So to find the direction, we're looking for this, and let me just call it phi instead of theta, just so we don't think it's the same theta as the given theta here. We're looking for phi. We're going to use the inverse tan of Fy over Fx. So we're going to plug in the inverse tan. And I usually just plug in the positive values because I just want a positive answer from the calculator. Otherwise, if you try to interpret the positives and the negatives that the calculator gives, it might get a little confusing. So I just put in the positive values and I get a value. I'm going to get 12.9 degrees. So that's not our final answer because we do need to picture exactly which way it's going. We know the net force is going down and to the left. If we say that our final answer is 12.9 degrees, then that means that our force would be going to the right and upward. That would be 12.9 degrees because that's the convention for a positive angle, is that it's defined from the positive x-axis going counterclockwise. So we have a few options. We cannot say 12.9 degrees because that's definitely not the correct direction. So let's erase that. What we can say is we could say 12.9 degrees below the negative x-axis. We could say that. The negative x-axis. Right, this would be the negative x-axis and we're going below it. Or what we could do, which is more typical, we could say that we're going to define our angle from the positive x-axis, and we're going to define this angle here from the positive x-axis all the way to our vector. That's going to be our phi. You can see from this picture that it means that we have a straight line, which is 180 degrees plus the 12.9 degrees. So we would say that our angle is 192.9 degrees. And we would want to say this when the question says, what is the angle with respect to the positive x-axis going counterclockwise? That would be our final answer. So I know this was a long video, there were lots of steps, but this is a really important type of problem using vector addition. If you struggled, you're going to get plenty of practice. And also, once we get to electric fields, we're also going to do more practice using vector addition to add fields rather than forces. So keep that in mind and keep practicing, and I will see you in the next video.